All right, so today we're going to be talking about what's called a definite integral. And a definite integral is capable of calculating the exact area under a curve. So we're not talking about approximation method. We're talking about exactness. Okay? I want to remind you that the right Riemann sum, of a function from a to b is just the sum of the areas of n rectangles between the curve and the x-axis from a to b. So what we're saying is, you can go from a to b, and there's all these rectangles, right? And if you're doing right rectangles, they kind of look like this, And here I've drawn 3 of them, but you can certainly draw more. And let's just say there were n of them. Each one has a base and a height, right? So if you want to measure the base of one of these rectangles, you would want to know how long a minus b is, right? And then you want to know how many rectangles there are in this space. So right now, I've got 3 rectangles packed into this little space. So each one would be b minus a over 3 in terms of its width. But if I put in 100 rectangles, then they would be b minus a over 100. Each one would be that wide, see? So what we're saying is that we can define the width of each rectangle as b minus a over the number of rectangles available. And for this class at this time, we're going to assume that the rectangles all have the exact same width. Okay, because some people actually draw these rectangles where one is skinny and one is wide, but we're not doing that here. It makes for a very confusing discussion. Also, the height of the rectangles all vary, I mean, some of them might be the same, but there's no reason for them to have to be the same. You have a curve, and so as you go through, each rectangle has a different height, even though they're all the same width. And that height of that rectangle is dictated by the rises and falls of that function. So, in a very real sense, we can say that the height of each rectangle is f of x. Wherever you're at, that's the height. Okay, so it turns out that it's actually f of c, where c is the rightmost value of x in the rectangle. So I'll just draw a quick sample here. This distance is now called delta x, and this distance is now called f of c. Okay, the height of the rectangle, f of c. Okay, and that's just one rectangle. We've got a bunch of rectangles. So with one rectangle, the height is f of c. Okay, so let's say you wanted to go ahead and collect all the rectangles and put them together. You could use like a sigma, The sigma just means to add them all up. So let's go ahead and look at the next part here. It says the right Riemann sum could be written as a summation notation. Big sigma, that kind of thing. So let's try that. We haven't done that in a while. So imagine adding up all the rectangles from I equals 1 to n, each one's length times height, or I should say height times base here. And I don't think I want to use just a generic x. I want to be specific and put a c sub I, because the x's actually change as you go along. Okay, so just another quick sketch. Let's say you're at A. Your first rectangle looks like this. See? The right side of this interval is C1. That's what it's called, C1, and the height is f of C1. So the width here is delta x, we call it. That's the width of the rectangle. The height is f of c1. The next rectangle over would be width delta x still, but height would be f of c2, and so forth. So how do you find like c15? Well, you would basically take a and you would add delta x to it 14 times, right? If you wanted to find, 15 times, because you would want to get, let's say, c15. That'd be way out here. C15 would basically be A plus delta x 15 times, if that makes sense. Okay, so C is just going to be A plus delta x multiple times, specifically I times. So it's going to be delta x added on I times to the A. And delta x, remember we said on the previous page, is B minus A over N. Okay, in this classroom, you don't need to memorize all of these details, like what CI means and what delta xi means. What you need to understand is that I'm trying to collect a bunch of rectangles all at once, and the best way I know how to do that is to use a sigma, because it kind of gets them all at once, you know? Okay. The drawing is optional there. I know you don't have a whole lot of space either. Okay, if you want to make a Riemann sum more accurate, like closer to the actual area, what's one thing you can do? Yeah, more rectangles, right? So another way is to switch from RRAM to MRAM, you know. But that makes a slight improvement. But if you really want accuracy, you need to increase the number of rectangles. And as you give it like, 1,000 rectangles, we saw the calculator even was adding so many carefully calculated areas, my calculator at least couldn't handle it. So, at least not in that current source code with that program I had. Okay, so we would like to make more rectangles. More rectangles means better area approximation. Ultimately, if you could make an infinite number of rectangles, I suppose you would get exactly the correct area, right? Does that make sense to you? If you could pack in an infinite number of rectangles, it would represent the exact area. Okay? So we would have to do that with a limit, because you can't actually make infinity of anything. So we would just start talking about what would happen if n went to infinity, and what would happen to, well, let's talk about this. What would happen to the width of each rectangle? You've got a graph, right? And there's only yay amount of space between A and B, and you want to put in an infinite number of rectangles? They're going to have to be pretty skinny, right? They're going to have to be really skinny. What's going to happen if you start packing in an infinite number of rectangles? What's the width of each one going to have to be? It's going to have to go to 0, right? So this is where it gets kind of hard to understand from a theory standpoint. But each rectangle will collapse to a width of 0 and yet maintain its height and an area somehow. Interesting. And the right Riemann sum would actually approach the exact area under the curve. So it's just an interesting situation. If the more rectangles we add, the more accurate our answer. So the logical conclusion to that is if we could put an infinite number of rectangles in, we get perfect answer. And that's correct thinking, although it's hard to understand because the rectangles all collapse down to a width of exactly nothing. Interesting. So the actual area would look like this. It would be the Riemann sum you saw a minute ago, I equals 1 to n. Right? We said that there's an f of c sub I here. That's just the length of, like the height of each rectangle. And then there's a delta x sub I here. That's just the width of each rectangle. And they're all the same width, so you can drop the I subscript on delta x. Delta x1 and delta x2 are all the same. But then we're going to throw LIM in front like this. This is new. LIM, n goes to infinity. And that's the exact area under the curve. Or between the curve and the x-axis. Okay, when you see it written like this, that's an n, by the way, not an h. Make sure that's clear. When you see it like this, know that some people actually prefer to write it a little bit differently. Instead of writing n goes to infinity, they'll write delta x goes to 0. It's the same thing, because when you make an infinite number of rectangles, the delta x collapses anyway. So just know that you might see it with the green instead of the red. But honestly, no one leaves it like this for very long anyway, because we then change it to this brand new symbol, a stretched out looking S, with an A here and a B here, and an f of x here, and a dx here. This is a new symbol for us, and it's called the integral symbol. The LIM and the sigma right here, the LIM and the sigma together means that you're going to add up an infinite number of rectangles sum capital S. We stretch it out. I'm not really sure why we stretch it out like that, but it still means S. It still means sum. It's just an infinite number of objects. See, and each one's infinitesimally small. Now notice the f of x is still here. This said f of ci, and this now says f of x. And notice what happened to delta x. Delta is the capital Greek letter for d, right? That got shrunk down to just a d, lowercase d. So what's happened is your delta x's have all collapsed down to become differential in size, which means basically infinitesimally small, non-zero. So kind of a weird notation, that stretched out s, but you should know this, that still means limit of sigma. You should know that. You should know that that symbol just means limit of sigma. You hardly ever need to know that, but it's important to at least know it. Okay, how do you pronounce this thing? You pronounce it as the integral from a to b of f of x dx is how you say it. That's how you read it. And it can be interpreted as the exact area, the exact signed area between the curve and the x-axis. Now why do I say signed area? Because sometimes the area has a negative on it if it's under the x-axis, you remember. So signed just means some areas are positive, some areas are negative, like that. You already knew that. So you've probably seen this symbol before. How many of you have seen this symbol before, the stretched out looking S? At least on your calculator you saw it, right? So what is it? It's just the sum of all the rectangles. Or you could think of it as a limit as n goes to infinity of sigma. And let's just talk about the actual symbol one more time here. So this thing is called the integration symbol. Just like sigma, it's a command. It means do something, right? Like when you guys see d dx, and then there's like a sine x chilling here, you know you're supposed to do something, right? Well, when you see an integral sitting in front of a function, it means do something, okay? We'll talk about what to do on Wednesday, okay? But it has to do with finding area, and then these are called the limits of integration. This is the lower limit of integration. This, of course, is the upper limit. This is just your variable. The dx tells you, you know, like when you see d dx of L and then someone else writes d dt of L, those are two totally different things, right? So when you see the d dx, you're like, oh, that's like x is my variable. And then when you see d dt of L, you think, oh, time is the variable or whatever. That dx right there in the integral is also important. It tells us what the variable should be. Okay? Okay, so this is your variable of integration. And this part right here, do you guys remember what to call the inside of a square root? Does anyone know what this part's called? The radicand, right? Well, this thing is called the integrand. Okay, that's important you know that word because of all the vocabulary that I just wrote, that's probably the word that shows up the most. You'll see integrand, integrand, integrand. A non-zero integrand, positive integrand, you know. So you need to know that word very well. Okay, let's go to the next part. Okay, so some of this looks crazy complicated, right? But it really is very simple, okay? So just bear with me and let's get through it. It says if f is non-negative throughout the interval from a to b, so what does that mean? It just means it never goes under the x-axis. So a non-negative function would be something like this. Maybe it hits the axis, you know, but it never goes negative. It never goes under. So a non-negative function, if you're going from a to b and you're trying to evaluate an integral, what you're doing is finding this area. So what am I saying? I'm saying the area is positive. That's all this means. It's not that complicated. Look, it's just saying if the function is positive, then the area is positive. Yeah, we knew that. We knew that if you have areas above the x-axis, they're positive. Now it says could equal 0. Because I guess that area could be 0 if the curve is like right on the x-axis. What's this next statement mean? Well, let's see if we could pronounce it together. Everybody see if you can say this out loud with me. How do you say this? The integral from a to b of dx. Notice there's no f of x. That implies there's a 1 there, right? That no one would bother writing. So I'm going to put it in. What does it mean? It means the area under the line y equals 1 from a to b. So let's draw a quick sketch. Imagine graphing y equals 1. That's simple enough. Imagine doing so from x equals a to x equals b and asking what this area is. Well, how wide is this rectangle? B minus a. And how tall is the rectangle? 1. So what's the area? B minus a. This isn't that complicated. Right? Common sense. If you know what symbols mean. If c is a constant, and the integral from a to b of c f of x dx equals c times the integral from a to b of f of x dx. Whoa, what just happened? What did I do with the c that was on the inside of the integration symbol? I took it out, right? I took it out. Why am I taking it out? It's a limit. This is all a limit. Remember we did this with limits. You're always allowed to pull a number out of a limit. If you remember doing problems like this, limit of 3 rad x as x goes to 2, there's no reason you can't put the 3 out here. Be my guess. Well, this is a limit. It's a limit of a sigma. But you can certainly factor a coefficient out of a sigma. You did it last year a million times. And you can factor it out of a limit. So what we're saying is you have all my permission to factor a coefficient out. So you can factor out a coefficient. I'm giving you permission to do that. You'll be glad you have it too, especially when it's a negative number. If c is a constant, then the integral from a to b of c dx is c times b minus a. Well, a minute ago, there was no c here. Look back at bullet 2 up above, right? What we're doing is we're pulling out this c to the front because we have permission to. And we already said that the integral from a to b of dx is b minus a. So we are saying that the integral of c times dx is c times b minus a. Okay, here's what it means. Let's say you have a graph. I know there's not a lot of room. But you've got this line up here, y equals c. And you're going from a to b. And you want this area. Well, what is the width of this rectangle? B minus a. And what is the height of the rectangle? C. And so what's the area? B minus a times c. See? Okay, next is this one. This one's a little bit harder to explain now. But just know that if somebody flip-flops the a and the b around, then that produces an extra negative symbol. Okay? So the price you pay for reversing the limits is you have to reverse the sign of your outcome. And then the next one actually is very simple. This is saying the integral from a to a of f of x dx is 0. So why would that be? If you have a random function and you're going from a to a, you're not going to collect any area. You're not going anywhere, see? You're trying to measure the area at a. What's the saying? You have to go from a to b, and have like a sort of region you want area of. In other words, the area of that segment is 0. That little blue segment. The next one is just giving you permission if you run into a problem that has 2 functions in it, like this. Feel free to split it into 2 separate integral problems. So the integral of a sum, is the sum of the 2 integrals. And then the last one is saying this. It's saying, let's say you have a function like this, and your plan was to integrate from a to b. And you got this far, and you decide to stop for some reason. Maybe there's an asymptote, or maybe there's a hole in the graph right here. like a little hole. So you feel like you're supposed to stop when you get to here. So you stop at the hole, and then you decide, okay, I'm going to keep integrating on this side. So you stopped at the hole. And let's say the hole is at C. In your efforts to integrate from A to C, you got some of the area. And when you did your integral from C to B to finish things up, that's the blue part, you did this integral. Well, guess what? You just found the area from A to B, the whole thing. You just did it in 2 stages, is all. So this is what this is saying. The integral from A to B of f of x dx, sorry, a little sloppy there, is the integral from A to C, and then from C to B. So you're breaking the interval into 2 parts, and the integral then separates into 2 integrals. So you may separate the interval if you break the integral. You may separate an interval and break the integral into 2 problems. Okay? You might say, I would never do that. Why would I stop halfway? I'm a dedicated person. Sometimes you have to. Like if there's an asymptote, or if there's some weirdness at C, you might have to stop. But know that you can keep going, and it still makes sense. All right, all of that's very theoretical until we do something with it. So let's try some examples. So the first one, I should have typed the instructions, but the instructions say, write this limit as a definite integral. So here's how I do these problems. Let me let you copy it down real quick. Okay, what I would do on this is I would circle this part, the limit and the sigma, because that's your integration symbol. Okay? And then I would circle this part over here, the delta xi. The delta xi is your dx. Makes sense? Delta x, dx. So that's your dx. I would get that done first. Whatever's left over, that's your f of x. Okay? So this middle part I would do last. It looks like 1 over 1 plus x squared. So I color-coded everything for you. I started with the blue, then I jumped over and did the green, and then I figured out what was in the middle still. And now I need my limits of integration. Well, those are given over here. Make sure you put the smaller one at the bottom if they list it as an interval like this. There's the answer. So it's not too bad if you actually have done it or seen someone do it. Okay? And I'll show you a harder version of that next time, or maybe later in the week, maybe Thursday or Friday. I have a couple multiple choice questions I'll show you. They're very ugly looking, but you can kind of dissect them like I did. Okay, let's go on and try example 2. So now for example 2, we just want to understand what it means. It literally means graph the line y equals -2. Okay, so you don't have to graph it, but imagine graphing the line y equals -2. It would look like this. How do I know to graph that? You could tell from the integrand. The integrand is your function, see? This is your f of x. So imagine graphing -2, and then going from -1 on the x-axis all the way out to 9, and ask yourself, what is this collected area? It's 20. The area is that of a 10 by 2 rectangle. That's all it is. So the answer to this would appear to be 20, but where is it located? Where is this big rectangle located? Above or below the x-axis? Below, so you would need to give it a sign. Okay, the answer to this problem is actually -20.
So you have to add a sign based on where it is on the graph?
Yes, you have to make it a signed area. You don't want to put 20, it's wrong, you know. The other way to do this problem is to go ahead and treat it using the rules we had. I told you that if you see an integral from a to b, and there is a c here, You can find the answer by doing c times b minus a. C is a constant, of course. You can't do that if there's an x there, but if there's a c right here before the dx, you could just use this as if it were like a little formula. In other words, you could have solved this by doing -2 times 9 minus -1, -20. That's a little more formulaic approach. Let's look at number 3. Okay, first thing I noticed about this problem is I think it's weird how there's a 4 at the bottom of the integral symbol and a -1/2 at the top. It seems to me that they should be switched around, where the -1/2 is at the bottom and the 4 is at the top, right? You go from the lower to the upper, just like on a sigma. So the first thing I'm going to do is switch my integration limits around. And I'm going to put the -1/2 down here and the 4 up here. Now, what did I say you have to do if you decide to make that switch?
Flip the sign.
You need to negate everything. So you need to put a big fat negative there if you do that sort of trade. Okay, so let me put a big negative out there. And we said that if you have a constant of any kind, it can be factored out. Well, if this negative is out front, it obviously means -1. You could bring it right back in again and switch these around. So this could be 3 minus x on the inside. So I'm going to write it like this. I'm trying to get myself in a position where I understand the question, guys. Okay, so this is just the question. I think I understand it now. Oh, I meant to write it as x minus 3. Okay, x minus 3. So here's what it's saying. The question is saying, imagine the line y equals x minus 3. We all know what that looks like. Okay. Find the area between -1/2 and +4. Okay, find the area between -1/2 and +4. So we're talking about this area right here. I want that area. This is just two triangles. So let's just use our knowledge of geometry. The first triangle looks like this. It's actually 3.5 by 3.5 is the area, or the dimensions. That first red triangle. Why 3.5? Because it goes from -0.5 to +3. So that's a distance of 3.5 this way. Also, it's got a slope of 1, so these are all 45-degree angles. This is just a 45, 45, 90 triangle with side length 3.5, and this, of course, 3.5. And then there's that little triangle. That one's above the x-axis. That one looks like this. What are the dimensions on that little guy? That's just a little 1 by 1 triangle. So the area of the first triangle is 1/2 times base times height, which is 12.25 over 2, so 6.125. And this area of the second triangle is 1/2 times 1 times 1, which is 0.5. And be careful here, the first triangle is under the x-axis, right? So we have to give that first one a negative area, and the second one a positive area. And the answer comes out to negative. What's that?
Why is it 0.05?
I have no idea why I put an extra 0 in there. Half is typically written as 0.5 in most cultures of the human race. Just not in my case, I guess. Okay, so I'm going to use a calculator for this because I can't do this in my head for some reason anymore. Negative 5.625 is the net signed area. And that's the answer. And you have buttons on your calculator that could solve this for you. And if you type this question as is, it would give you this answer. So it'll be really easy to check your work. You can use Wolfram Alpha. you can learn to use your calculator. I was going to show you a little bit later how to use a calculator. But you could play around with it if you want. Let's look at example 4, and then what's going to happen is the bell's going to ring, and I'm going to just, after you leave the room, I'm going to finish this video and post it. Okay? So your assignment will be to finish watching this video and start on the problems that I assign. You'll see them on Edmodo. It's not due till Thursday. Just get the video watched, maybe start in on the easy area ones. And especially try to review what this all means before then, because you don't want to come back Wednesday clueless. Okay, so what does this mean? Well, on this one you can see the lower number here is -3 and the upper number is 0. That makes sense. Those are sort of in numerical order, so I'm going to leave it as is. I'm not going to switch those around this time. But I am going to notice that there are 2 integrands. See that? This integrand is a sum of 2 things. So I'm going to feel free to split this up into 2 problems. The first one is the integral of 2 dx. The second one is the integral of square root of 9 minus x squared dx. Okay, so this first one we can view as the area under the line y equals 2 from -3 to 0. So let's go ahead and look at it that way. So you do not have to draw these pictures, but if you can draw them, then you probably understand them. So there's the line y equals 2. I got that from looking at the integrand. And we're going from -3 to 0. So -3 to 0, trying to figure out this area here. Well, that's just a rectangle with length 3 and height 2, so this is an area of 6. And it's positive because it's above the x-axis. Even though it's on the left side of the y-axis, it's still above the x-axis. So this entire integral comes out to be 6, this first one. Okay, the second one is a totally different drawing. And this is just one of those functions you should know. This is the graph of square root of 9 minus x squared is the graph of a semicircle centered at the origin with a radius of 3. So some of you knew that, I could tell, in class, and others didn't. But that's an important one to know. And it's because y is square root of 9 minus x squared, because if you work this out and rewrite it a bit, it's basically x squared plus y squared equals 9. The top half of it. The top half of the circle. Okay. In any case, we don't need a lot of calculus or any calculus at all to solve the area of this, because this is literally a semicircle. Right? So if you want the area of a semicircle, just use pi r squared over 2. So it's just going to be area equals pi r squared over 2. Radius is 3. So 9 pi over 2 is your area there. And this one is done. You could put it in decimal if you like. Okay, let's look at another one. Okay, this one's a little bit harder to draw, but you can split it into 2 if you want to. I was actually just going to draw this thing and then look at it as one image. So you guys know that square root of absolute value x looks like this, right? The -3 and the +1 just shifts it to the right 3 spaces and up a space. So right 2, 3, up 1, puts the graph here. Like that. So it's shifted right 2 and up 1. And we're trying to find the area from 2 to 5. So instead of seeing this as 2 problems, I'm just going to see it as 2 phases of integration. So the first one is a little trapezoid there, right? And the second one is a little bit bigger trapezoid. So I've got the green and the blue outlined trapezoids. That's how I plan to do this problem. Okay, so I'm going to treat the integral from 2 to 5 as 2 integrals. Integral from 2 to 3 first. That's the green picture. That's from 2 to 3. I'll color code these limits. And then as a separate integral, I forgot my absolute values here. There we go. From 3 to 5. And these are just two trapezoids. You kind of have to measure them carefully. The green trapezoid looks like that. And this distance is actually 2, and this is 1, and this is 1. So the area of this thing is 1/2 times base 1 plus base 2 times height. So that's basically 3/2. And then the blue one is bigger looking. This is a 3, 1, 2 rectangle, or trapezoid. So the area will be 1/2 times 1 plus 3 times 2, which is 4. So the answer to this, since both of these are above the x-axis, I can just add them together. 3/2 plus 4 is 5.5. And you might notice that in the back of the book, they stuck everything as fractions. So 3/2 plus 4 is, 11/2. So they might leave it like that. Okay, this one's a little bit more confusing just because there's fewer numbers. And it looks like the integrand is 2t. So since we don't know t, we're just going to draw the line, y equals 2x, sort of, y equals 2x. So I'll label everything the way it should be labeled. This is t, and this is the line y equals 2t. And we're going from an arbitrary a value to an arbitrary b value. And I chose to draw them on the right side because I think that would help you understand it best. But you could draw the a and the b anywhere you want, as long as you understand that it should work in my case too. So here's my drawing. What exactly is the area of this trapezoidal region? And by the way, if you straddled the origin here, you have a slightly different picture than I do. You would have, let's say you chose to draw from A to B like this. You can draw this picture if you like. I just thought it was a little more confusing. Okay, well in any case, we know the coordinates of this first point here are going to be a comma 2a, right there. And the coordinates of this point are b comma 2b. See? So you could say that this trapezoid here in blue has legs 2a and 2b. As for the width, or the height, I guess you should say, of the trapezoid, that's the distance between the two parallel bases, that is b minus a. Okay, so altogether the area is, and we're not going to write a if we can help it, we're going to try to use our new symbol, right? So in the integral from a to b of 2t dt is 1/2 base 1 plus base 2 times height, and this just gives us a plus b times b minus a, which is just b squared minus a squared, like that. Okay, for our next one, we're going to go ahead and do this one, and I accidentally put the x squared on the bottom. I meant to put the x squared on top. Okay, so you'll notice that this is kind of a confusing one because the graph itself is hard to draw. 1 minus, or it would appear to be, 1 minus x squared over 1 minus x would appear to be a complicated graph, right? Until you factor it and you realize exactly what it is. So here's your integrand. It represents your function. Sorry for the typo. The square's on top. And this factors into 1 plus x times 1 minus x, and this is all over 1 minus x. So this cancels out. And we see this really is just the function y equals 1 plus x with a hole at 1. Hole at x equals 1, see? Okay, so I'm going to go ahead and sketch it. It's the graph of 1 plus x. And then right here at x equals 1, I need to punch a hole in the graph. Right there. Put in a little hole. There we go. Okay, and then my goal was to find the area, the signed area between -2 and +2. So basically it's this area and this area, and I just feel obligated to stop here at x equals 1 because there's a hole in the graph. So I got the two red areas and this green area. Why don't we do 3 different colors? So we'll do blue, red, and green. Okay? All right, now these are the red triangle and the blue triangle, both 45, 45, 90 triangles. We know that because this line has a slope of 1. So since the slope is 1, that means that the angle formed against the x-axis is 45 degrees, as you probably are well aware of. So what I'm going to do is just assume that these are all 45, 45, 90s. Here's my blue triangle, and it's a 1 by 1. And then there's a red triangle, and that one is 2 by 2, actually, because we're going from -1 all the way out here to past the y-axis to +1. So that's 2 spaces across, and of course 2 spaces up if it's 45, 45, 90. And then glued to that, there's a trapezoid where this is 2, and this is 3, and this is 1. If you don't believe me, you can plug numbers into the function also to get the various heights of these. Okay, the blue area is going to count against us as we tally the total area. So here is the integral from -2 to 2 of 1 minus x squared over 1 minus x dx. And this is a negative area first because we have a blue triangle under the x-axis, and it's going to be 1/2 times 1 times 1 is its area. And then we're going to switch to the red triangle. The red triangle is above the x-axis, so it's positive. And it's a 2 by 2 triangle, so it's 1/2 times 2 times 2. And then we're going to go on to do the green trapezoid, whose area is 1/2 times 2 plus 3 times 1. So altogether, this integral turns out to be -1/2 plus 2 plus 5/2, which is 4. Turns out it's 3/2 plus 5/2, 8/2. Okay, now you might say, hold on, Mr. Short, why did you stop at the hole? And here's the reason I stopped at the hole. I stopped at the hole because technically integration is only defined when you have a continuous function. So anytime you hit a discontinuity, whether it's a hole or an asymptote, you need to kind of stop. It turned out that the hole itself does not reduce the total area by any amount. The area under the hole is exactly 0. So the area between that hole, I'll go ahead and highlight in purple. The area between this hole and the x-axis is 0. So it's not like it took away any of our area or changed our answer at all. But as a formality, know that you should stop when you hit a discontinuity and then integrate around it. Turns out that everything kind of stacked up nicely, and you really could have solved this entire part in one step. Let me show you what I mean. The triangle, the red triangle and the green trapezoid could have actually been treated as one conglomerate object. You could have done the area of this triangle. It is a 3 by 3 triangle. That would have worked, but it's a little bit informal to integrate through a hole like that. Okay? So it's just a formality, but you would get the right answer. Okay, the next thing you need to know is that you can use a calculator. Okay? You can definitely use a calculator for integration. All right, so we want to know how to do everything without a calculator too, if possible. But right now, we don't know how to integrate certain types of areas. For example, how would you find the area under, or on a cosine wave, between the x-axis and the cosine wave? So how do you do that? So what we're going to do is just use our calculator for that. And we're not going to use a program that we downloaded. Actually, your calculator already had it built in when you bought it. Okay, so what we're going to do is turn this thing on and go into home screen, actually. And make sure it's in radians, because we said before that integration, or the derivative of sine is cosine, that sort of thing, only if you're in radians. So we want to be careful to keep our calculator in radian mode. Okay, and then even from the home screen, though, you can press Math 9, and it will pull up this. It's
Some of you have something a little more fancy. It looks actually like an integration symbol. But then you're just going to type the function. So cosine x. Okay, and then you're going to put comma, and then it says dx right here. So you're going to do x. You can't type dx, you just type x. You're telling the calculator to integrate as if x were the variable. And then you're going to type your two limits. So another comma, I just put another comma there, and then the limits were 0, and then comma pi over 2. Okay, so cosine is the first thing you type, that's the integrand. And then the variable of integration, x, and then the a and the b value. Everything's separated by commas, and then press enter. Except mine didn't work. I think I have too many parentheses. There we go. 1. Interesting. So what we just found is that this area here is 1. Okay? So the answer is 1 minus 1, which is 0. And that's the answer. Okay? So calculus is kind of neat. You can use that. Some of you have the newer operating system, so when you press Math 9, you get this, and it's sort of a fill-in-the-blank ordeal. So what you need to do is you need to put a 0 here, a pi over 2 here, a cosine x here, and an x here. So just type it in the same way you would write it on paper. It's a little more sophisticated software there that the TI upgraded to. Okay? And the last one is this one. This is a little premature to be explaining this, but this is talking about a sine wave. So the sine wave is the dark black one. And the cosine wave, that's this blue one. And we're only going to be looking at the portion between pi over 4 and 5 pi over 4. As it says right here. There's a graph of x equals pi over 4, that's this line. And the graph of x equals 5 pi over 4, that's this line. Like that. Okay? Oops, I'm sorry, 5 pi over 4 is further out. I just drew 5 pi over 4 right on top of 3 pi over 2. Here we go. This is 5 pi over 4. Let me redraw this part just a little bit here. Make it look a little nicer. So between these two green lines, and also enclosed between the two curves, what is the area? So we're talking about this area right here. See? Okay, so what I'm going to do is I'm going to notice that the upper curve, the curve that's higher up in this region is the sine wave, and the curve that's lower down in this region is this cosine wave. So to get the area between them, imagine putting your rectangles in. Your rectangles would look something like this. The top and bottom of the rectangles are not the sine wave and the x-axis, but rather the sine wave is the top of the curve, of the rectangle, and the cosine wave is the bottom of the rectangle, see? So the heights here, each height is basically sine minus cosine. Okay, so I'll just try to prove that. So this is like the point A comma sine A, and this point right here is the point A comma cos A. So the height of this segment, or this rectangle, would be sine A minus cos A. And it's even true when you're straddling over the x-axis. So let's say that this is A sine A. This point down here would be A cos A. So this distance, or the height of this particular rectangle, is sine A minus cos A. So what we can do is just basically extend our understanding of the integral. Instead of going from pi over 4 to 5 pi over 4 sine x, or cosine x, we'll do both. Sine x minus cosine x is the height of each rectangle. The dx, remember, represents the infinitesimal width of each rectangle. And now we can just simply type this into the calculator. So I typed it earlier and I got negative 1.828. All this means, the reason it's negative is because the majority of this red area fell under the x-axis. There's a piece above it, but it's not quite as big. The piece below it is a little bigger.
And that's the answer. And that's the lesson.